Okay, so now we've seen how to do the profit maximization problem for a firm in the short run where they only have to choose one of their inputs. We did labor. We've done it in the long run for these kind of standard capital and labor production function that we've been using through this course. But what if you want to go beyond that? What if you want to have a production function with lots of different inputs? Because for some reason it's important for you to model all these different things. As I've said before, if that's the case, then that's no problem at all. It's fine for you to have a production function with as many inputs as you want. So instead of using capital and labor, let's use just the generic x. So you have input x1, x2, x3, and let's keep going all the way out to xn. So you just have lots of inputs that are needed to make this output. And that's realistic, right? You need electricity, materials, all this other stuff, and there might be all sorts of different kinds of things, and so the production function in the real world might be really complicated. How does that affect the firm's profit maximization problem? Well, let's say the price of any input, so to represent any of these inputs, I do a little x with an I, and I can be replaced by 1, 2, 3, or anything up to n. So the price of xi is going to be pi, okay? And profit is now going to equal the price of your output, there's no little subscript here, times the quantity of the good you produce minus your costs. But instead of writing WL plus RK, I'm not going to do that now because those are not the inputs that I'm spending my money on to create this output. Instead, I'm spending money on X1, X2, X3, X4, X5, all the way up to Xn. And as I said before, X1, we're going to say the price of that is P1. So the amount I spend on X1 is P1 times X1 plus P2 times X2, all the way out to Pn times Xn. Okay? And as I mentioned earlier, a better way to write all this is with the summation script. So this symbol means the sum of terms, and each term you replace the I with a 1, 2, 3, all the way up to n. Okay? And the Q we're going to replace by this guy here. And so our profit function looks more like this. Price times f of x1, x2, x3, xn, minus the sum of spending on all inputs. Okay? So this is our new profit function, and it looks a little different, but it's still the same basic idea. How do we then find the profit maximizing point? In this case, that problem is, we have to find the optimal quantity of all the things that we have choices over. In the first short run case, the only thing we could choose was labor, so we had one choice. The second, we had capital and labor, and now we have n things to choose, where n is whatever number of inputs are available to us. But the thing is, we're just going to still use the same tricks as before. We're just going to take the first order condition for every choice variable. Each one of those we're going to set equal to 0. And then we're going to basically solve the ensuing system. Okay? So let's just do a quick sort of mock-up of what that would look like. The partial derivative of profit with respect to good x1 is going to be equal to the price of the output times the partial derivative of the production function with respect to x1 minus, well, we've got all these costs added up, and if you're not used to that summation script, it might be easier to see if you look back here at this guy. And you can see that the derivative of everything inside the parentheses There's an x1 here multiplied by p1, but then there's no other x1s. So this is just going to be minus p1. The next one is going to be the partial derivative with respect to x2, and that's going to equal p, the partial derivative of the production function with respect to x2 minus p2. And we have to do that over and over again. And eventually we get to the last one, where we're taking the partial derivative with respect to the last input, x sub n. And we've got p times the partial derivative minus p of n. Step 2 is we set all these things equal to 0. And step 3 is we solve the system. I'm not going to do an example because it's just kind of tedious, and it illustrates the same kind of stuff that we did for the case of 2 inputs, but you basically use the same kind of approach, okay? And I just want to point out 2 things. First, notice that if we solve this, we can rewrite this as p times the marginal product of x1, because that's the derivative with respect to x1, has to equal the price of x1. This is the same thing as we've seen over and over again. You always find a point where if you buy any more of that product or of that input, the extra increase in sales that it gets you is exactly offset by the cost of buying that. And so you're going to do that for each of these goods. It's not just for capital and labor. It's a generic rule of optimization, of profit maximization. The second thing to notice is that we now have n inputs, so we can't graph this in any kind of 2x2 or like a, 2-dimensional space. We need an n-dimensional space to graph this. But pick any 2 of these points, like let's suppose we decide to pick these 2. Well, we could draw a isoquant and isocost curve for just these 2. That would be having to hold all the other ones constant and fixed at some value. And we could imagine there's an isoquant, and we could imagine there's an isocost curve. And this diagram would suggest to us that we would want the marginal rate of technical substitution for xn and x1 to be equal to the price ratio of these 2, okay? And we see here that that's exactly what we get if we do this algebraically too. If we divide these guys by each other, these p's cancel out, we stick a negative sign in front, and we end up with the marginal rate of technical substitution between x2, I guess this should have been a little 2, guys, sorry, and xn. Although it looks like I got my x's flipped. So one of these is, I have the n first here and the 2 first here. But anyway, it's the same idea. So those kind of rules, that's like why it's enough to use 2, because that kind of illustrates these points, but you would get the same kinds of intuitions if you went to an n-dimensional system. So that's it. That's the way that firms decide how to behave when their goal is to maximize prices and markets are competitive, meaning that they don't have any choice about the prices they face. They don't have the ability to, if they try to charge a price different than the prices offered, they just aren't going to get any buyers in the market. The next unit will be about using kind of the similar machinery to talk about consumers, and we'll see that we can't just exactly port over our math for firms to consumers. We're going to have to do a little something extra in this case.